Okay, thank you. All right, so we would like to approximate it with a polynomial. Now, what degree polynomial do y'all want to try? Because we could try to approximate it with a line, but would y'all agree a line wouldn't be that good? I mean, a straight line, if I try and draw a straight line there somewhere, like let's say, if I try and draw a straight line like this, I mean, that's kind of close to sine, isn't it? But it's not that great because it doesn't curve at all, right?
What about x squared times negative x squared?
Like 2x squared.
Maybe we could do a quadratic. You don't want to try a quadratic to start?
Kind of like together.
Okay, let's try a quadratic. We would like to approximate with a poly. Let's make it a quadratic. Okay, so we've just made a decision that we're going to try and approximate the sine function with a quadratic function. So g of x, if it's a quadratic function, has to look like this: ax squared plus bx plus c, because all quadratics look like that, don't they? Yes?
Yeah.
Okay, so
Yes.
our goal now is to figure out what a, b, and c are, so that when we graph it, it looks like this function, this blue function. Let's go for it. So here's what I'm going to do next. The second thing I'm going to think about is we want the value of the sine function at 0 to be equal to the value of our quadratic at 0. So think about what I'm saying there. Can someone explain to me in layman's terms what I just said by writing that mathematical statement down?
We want when you plug in 0, the sine and g to be equal.
Yeah, you basically want them, both of these functions, to coincide at 0. You want, when you plug 0 in, that you get the same points. Right there, I just did it in red. Do y'all see that? We would like for them to have the same values at 0. Okay, well, what does that mean? Well, do we know what sine of 0 is?
0.
0. Okay, so we know sine of 0 is 0. And what would g of 0 be? So remember, this is g of x, right? Right here. So what would happen if you plugged in 0 for x there? What would you be left with?
C.
C. So we just actually figured out what c needs to be, don't we? Don't we know that now?
Yes.
Like if c is 0, then both of these functions will have the same value at 0. Now I still don't know what a and b are, right?
No.
Okay, that's okay. I mean, at least we've got this much. So how would we go about the next thing? Well, maybe the third thing we would do is we wanted them to have the same value at 0, but we also want this to be true. So someone explain to me in layman's terms what that statement says.
You want the derivative of the sine function to equal the derivative of the g function?
Yeah, so we want, I mean, we already know that they're going to have the same point at 0, right? They're going to have the same y value. But wouldn't it even be better if they both had the same tangent line at 0? Like have the same slope? Like that'd be really good, wouldn't it? So let's do that. Let's first of all, let's take the derivative of sine. So we want to know what this is. But let's first figure out what is the derivative of the sine function. We know that already, right? That's just cosine of x. And do we know the derivative of the g function? So what's the derivative of the g function?
2ax plus b.
2ax plus b. And so now let's go and do this equation to try and make them true. So what would the derivative of sine be at 0? That really means plug 0 into cosine, right? Because that's a derivative of sine. So what is cosine of 0?
1.
1. 1.
Okay. And we want that to be equal to the derivative of g, which is this function, when we plug in 0 for x. So what happens if we replace that x with 0?
Okay.
Yeah. That would be b.
B. So now we know what b needs to be, right?
Mm-hmm.
Okay.
You take a second
Now,
derivative?
yeah, so why don't we try and make their second derivatives match too?
That's smart.
Okay.
So we go to the fourth And we want the second derivative. This is kind of really bad notation. The second derivative of sine at 0 to be equal to the second derivative of the g function at 0. So we need to know what their second derivatives are. What's the second derivative of sine?
Negative
That's
sign.
terrible
Negative
notation.
sign.
Sine x.
Negative sign, right? Negative sign of x. And what would be the second derivative of the g function?
2a.
2a. Okay. So now what I'll do is I will figure out what this is. So I'm going to plug 0 in to the second derivative. So I plug 0 in right here for this x in red there. Sine of 0 is already 0, right? So the left side here is 0, right? And then what's the right side?
0.
Careful, we're plugging in 0 for x, right? And there is no x
Oh,
here,
okay.
right?
Yeah, so 2a.
So 2a. And then can we solve for a?
Yes, by
Let's
dividing
divide by 2.
by
Zero.
You
2.
get a is 2, right? I mean, sorry, a is 0. So that's it. Why am I not going to keep going right now?
Because we found each variable?
We found them, right? Because we said we wanted to approximate it with a quadratic. We made that decision early in the problem. We said we're going to try and approximate sine with a quadratic. So we made them match, right? At 0, we made their first derivative match at 0. We made their second derivative match at 0. But the thing is, we started with a quadratic, didn't we? So if we take two derivatives, we're down to constants, aren't we?
Yeah.
Mhm.
Yeah. So I mean, there's no more for us to do. If we continued this process, we would basically get zeros. I mean, we wouldn't. There's nothing else to solve for. Okay. Does that all make sense?
Yes.
Okay, so
Yes.
let's see if we can't. That was all your grades.
Oops.
I may not be able to post this recording now. Oh well. Okay, let's do this. Okay, so there's the sine function. Yes. Oh wait, you know what? Let me go back to my notes. So what is the quadratic that we found? Let's actually write it down. What did we find g of x should be? So we said a is 0, right?
Yeah, so it's
Yes.
just B.
So that's 0x squared, and then we said b was 1, so plus 1x. And we said c is 0, right?
Mm-hmm.
So what's our quadratic?
Just
Well,
x.
it's just x, which isn't a quadratic. But what's happening here is by going through this process, we're saying, hey, we're trying to approximate sine with a quadratic. And by doing this process, the result is telling us, hey, look, the best you're going to get is to approximate it with x. That's your best approximation of sine if you're limiting yourself to a quadratic, is just the function x. So let's graph it. If I graph the function x right here, there it is, right? This is x. Is that a pretty good approximation of sine as you're close to 0? Let me zoom in. I'd say they're pretty good, right? They're pretty good approximation. Now, as you get further out, that approximation starts to suck pretty bad because sine curves away and your line just has to stay straight. So maybe we can get a better approximation. How do you think we could do that?
Go to a higher power.
Yeah, why don't we do it, instead of doing a quadratic, why don't we do a cubic, right? So let's start the whole process over. Let's just go to a new page. And this time, let's try a cubic function. And let's call that function g of x again. And let's call it ax cubed plus bx squared plus cx plus d. Now, we're trying to approximate the function sine, right? So sine of x. And I'm going to do the same thing. I'm going to be taking derivatives. So let's just list out the derivatives of this thing. This is f of x. We already know the derivative of that is cosine x. We know the second derivative of that is negative sine x. And I should be able to get one more derivative because I'm approximating with a cubic, so I should have one more power to work with. Does that make sense when I say that?
Yes.
Okay. All right, so those are going to be my derivatives of the f. Now let's look at g of x. Let's just list out the derivatives of g of x. So g of x is this guy up here. Its derivative, first derivative is 3a x squared plus 2b x plus c. The second derivative would be 6a x plus 2b, right? And the third derivative would be just 6a.
A plus.
2b is a constant, so the derivative of that would be 0.
Right.
Okay, so now let's play the game. First thing we're going to do is we're going to match. We're going to make our sine at 0 be equal to g at 0. We already know sine of 0 is 0. And what would this g function be if we plugged in 0 for x? D. We just get d, right?
Yes.
If we replace all the x's with 0. Okay, so we know what d is. All right, now let's go to the second step. We're going to need the derivatives to be equal, right? At
Right.
0. So we want cosine of 0 to be equal to the derivative of g at 0. Cosine of 0 is 1. The derivative of g at 0 is what? So you're now looking at the derivative here, plugging 0 in.
Cubic.
C.
Just c, right? So we now know c is 1. Okay, now let's do the third one. So third piece here, we know we want the second derivative, which is negative sine of 0 to be equal to the second derivative of g. Sorry, I should write it this way. The second derivative at g at 0. So we already know sine of 0 is 0. And second derivative at 0 would be what?
2b.
2b. And that means that b is 0.
The hell?
Right.
Okay. And then we do the fourth one, right? And now we need the third derivative of f, which is negative cosine at 0 to be equal to the third derivative of g at 0. What is the third derivative of g at 0?
6a.
Just 6a. And this side should be negative 1, shouldn't it?
Yes.
Cosine of 0 is 1, and there's a negative out front. And this we said was 6a. So what's a?
Negative 1.
Negative 1 6.
Negative 6.
Okay, we've got everything. So our function should be a, which was negative 1/6 x cubed plus 0x squared plus 1x plus 0. Do y'all see what I did there? Just replacing a, b, and c into this thing up, this thing way up here.
Yes.
Yellow. Yeah. Okay. Shall I go graph that? See how good it is?
Yes.
All right. Let's see. It's negative 1/6. Let's get. Well, we'll leave that one there. Negative 1/6 x cubed, and then what?
With x.
Plus x.
Yes.
Yeah.
Ooh, check that out.
Ooh.
That's better, isn't it? Isn't
Yeah.
that better? So where our line started to like break away from the graph because it couldn't curve, this cubic function actually starts to fit to that curve pretty good. Now it does start to lose it here in this region, right? We start to get worse. But how do you think we could fix that?
Go to higher power.
Go to a higher power, right? Maybe a fourth degree polynomial?
Is there a limit to how many powers you can do?
Well, what do you think we could actually do to make it match exactly?
Infinite power?
Infinite powers. Perhaps a series of powers,
Oh.
right?
I got you.
Got it?
Sure.
A series of powers. So look at this. I've already set it up for us. Okay, so what I want you to do here is pay attention to this.
Featuring the platinum band.
Whoa.
We're going.
What the hell?
Sorry.
That sounds like you're excited about this. Okay.
I am.
So here we go. We're going, just ignore this, okay? This is actually the power series for sine, but just pay attention to what happens. You see that right there? That is our first approximation we got, right? We said we're gonna try quadratic, and that's what we got.
Just
and then we
X.
tried a cubic, and we got that, didn't we?
Mm-hmm.
And then what would happen is if you keep doing this, I'm going to zoom out. Okay, remember the green one is the real function. The red one is us just going and finding higher powers. Just watch this. This is just freaking beautiful. Watch. You see that?
Oh, wow, that's
As I go
cool.
out, the more powers I go out, the better and better my approximation becomes. So now, would you agree that at least close to 0, we've got a pretty damn good approximation of what's going on? You could even say, like, even in this range, like -5 to 5, we've got a good approximation. It's a polynomial function, but it is a good approximation. Now, I stopped this so, but I could keep going. I can make this go out as far as I want. Okay? And if you don't believe me, I'll just keep doing it. I can just keep going. I think the website's having a little trouble keeping up now because there's a lot of computation going on here. But that's pretty cool, isn't it?
Yeah.
And so we have to kind of take a step back because what we're doing here is to approximate a given function at some point. I'm just going to call it a. Okay, for us it was 0, right? To approximate a given function at x equals a with a polynomial, we only need to know what? It's a lot, but it's a lot that we have to know, but
The derivatives.
we just need to know the derivatives, right? We just need to know the value of the derivatives of the given function, okay, of function at a. So as long as you can take derivatives of the function and plug the number a into it, for us we're plugging in 0, then you can always sit there and play that game of trying to get the coefficients, okay? So let's go back to sine of 1. You know what, I'll go back to the page that we started this with. Nope. Right, remember the sine of 1. Okay, so what did we say was our approximation, our cubic approximation? It was -1/6 x cubed plus x, right? So on your calculator, I want you to do this. I want you to plug in 1 into this. And so you're going to do -1/6 times 1 plus 1.
Like on the graphing part or just?
No, just evaluate this.
Oh,
This is
okay.
-1/6 plus 1. That should be just 5/6.
0.83 repeating.
0.83. So this is going to be equal to 0.83 repeating, right? Now, is that a good approximation of the 0.84? No, not really, right? But are we close to 0? Are we plugging in a number close to 0?
No.
Yes.
No, I mean, we're at 1, right? So let's try something else. Let's try on our calculator sine of, how about 0.1? So do that on your calculator first. I'm going to get 0.0998334 166. But if we use our approximation function, then we're doing -1/6 times 0.1, what, cubed plus 0.1. So I'm doing that on my calculator.
Point zero niner niner 83 repeating.
Say it again. 0.0
9983 repeating.
833 repeating. Is that a pretty good approximation? Well,
Yes.
we've got the first, what, we've got the first 6 decimal places in common. And that was just with a 3rd degree polynomial. We could easily go and try and get a 4th degree, 5th degree, 6th degree, 7th degree, 8th degree. And then if we could just wrap our heads around the idea of having an infinite degree polynomial, then you actually are saying that sine is that polynomial. That's what we will conclude with later on, but we will say that the sine function, and we'll learn this later, we are going to learn that the sine function is actually 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus 1 over 7 factorial x to the 7th. Do you see the pattern? 1 over 9 factorial x to the 9th plus ... Oop, hold on, I missed a minus here. This was a minus. So do y'all see that this right here is an alternating, it's an alternating series, right? Alternates plus, minus, plus, minus, plus, minus, plus, minus. Do y'all see these first 2 terms? Isn't that what we had already got that, right? Because what's 3 factorial?
6.
It's 6. Where did our 6 come from? Hold on, let's go back. Where did our 6 come from? Well, we took the derivative, didn't we? Look, we started here.
Yep.
And we took the derivative, right? So a 3 came out. And then when we took the derivative again, what pops out? That 2 comes out, doesn't it? So I could have rewritten this as a 3 times 2, which is 3 factorial, isn't it? And if I were to have started with the 4th degree polynomial, then a 4 would have come out, then a 3, then a 2. So it would have, it's basically perfectly suited for factorials. I hope you can see that. We'll have more practice with it, but. So we're going to discover that the sine function is actually equivalent. Okay, the sine function is equivalent to this infinite power series. All right. All we've shown today, at least up to this point, is that it's at least close to that, right? Point this out right now. Do you remember in pre-cal the idea of an odd function and an even function? Right, remember that concept in algebra, college algebra? And in pre-cal we talked about odd and even. Do you remember people saying to you that sine was an odd function? And they told you that because they said that sine is odd because if you graph it, it's a reflection over the identity. So here's the sine function. If you were to take the right side of it and reflect it over the y-axis and then follow that by the x-axis, you get this piece. It's like a double reflection. And so in algebra, you're taught that odd and even comes from this idea of reflections. But we're now in calculus. And do you see now why it's truly called an odd function?
Is the coefficients, right?
Yeah, I mean, look at all the powers. All these powers are odd powers. And any function, okay, any function whose power series has only odd powers would be an odd function. Does that make sense? I mean, it's not a mystery why we call it odd anymore. It's because its power series has odd powers. And so cosine function is even. So you should expect that the power series for cosine would have just even powers. All right, so we will get to more of this later. This was just to motivate the idea of where all this comes from. We need to actually back up and start, defining things. So let's back up. All right, so here we go, power series. So a power series, this is a definition, a power series centered at A. So I want you to kind of clear your minds with what we just did with the sine stuff, other than to realize that's where we're headed. But just kind of act like this is the first time we've talked about this. A power series centered at A is a series that has this form. You have summation, and please note that our summations are now going to start at 0 for power series, and they go to infinity. And then what you have is C sub n. C sub n is just a bunch of coefficients, just a bunch of numbers sitting in front of x minus a raised to the power n. So you can start doing this yourself. If you plug in n equals 0 here and here, you would get this first term right here. So that would be c sub 0 x minus a to the 0, but x minus a to the 0 goes away. That's a 1. So you just get c sub 0. If I plug in 1, I get c sub 1, x minus a to the first power. So there's really a first power here. I don't need to write it. And then you plug in 2, and then 3, and so on and so forth. So the number that's sitting there next to x, right here, that's where we say the series is centered. You may also hear this, or you may see this terminology, the power series about. Oh my goodness. The power series about A. X equals A. These mean the same thing. If someone says, hey, that's a power series about A, or that's a power series centered at A, then they're synonymous. So A is always some given constant, and X, very important here, X is a variable, okay? A variable. Now, this is a general power series centered at A, but whenever A is 0, so if we replace this X, this A here with 0 into this formula, then all you're gonna have when you replace these A's with zeros is this power series. So all that happens is this goes away, and you have this. And then when you write out the terms, it looks like this. So they call it a power series because it is just a series with a bunch of powers of x. Now, when we were just doing the example with the sine function, we approximated it with a cubic. I didn't call the number in front of x cubed c sub 3, did I? What did I call it?
C? Oh, wait, A.
That was A, right? And then this right here, I called that, what, B? And then this one was really C, and then this one was D, wasn't it? But if this is an infinite series, we can't use letters A, B, C, D because we run out of letters, right? We only have 26 letters. And so subscripting is much better. All right, let's take a look at a first example of a power series. All right, so our first example. Is this going okay for everyone? You all right?
Yes, sir.
Yes.
Okay. All right, so what I'm going to do is I'm going to take our general formula for a power series, which I'm going to put here in this little red box. That's our general formula for a power series centered at A. And I'm going to tell you right now that I want all of the coefficients for every single term. I want every coefficient to always be 1. And I'm also going to tell you that I want A to be 0. Then that means that this C sub n never changes. As you plug in different values of n, it's always going to be 1. And the A right here is always going to be 0. So if that's the case, if this is 1 and that's 0, then that really just becomes x to the nth power. Do you all see that? Okay, I'm gonna assume yes. And then plugging in n, like replacing n with 0, then 1, then 2, we get this right here. And of course, x to the 0 is 1, so that gives us this. And it goes forever, of course. So that is me giving you a specific example of a power series. That's your first real like example. It's not a complicated power series. And the reason it's not complicated is because I'm telling you that C sub n is always 1. Okay, so your coefficients in front are never changing. They're always 1, 1, 1, 1. It would be a more complicated power series if that coefficient changed every time you went out. But in this problem, it's 1. And then also the fact that a is 0 means that you don't have like a binomial to expand. You just have x to a power. So I now have a question. For what value or values of x will this series converge? Okay, so now we're talking convergence. All right, let's try this first one. So everyone, hopefully you understand that we're looking at this series right here, which comes from that formula right there. And what I'd like to ask first is what happens if x is 2? So tell me what would that series look like if x is 2? Sum n equals 0 to infinity of 2 to the n, right? Which is just 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus dot, 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 dot. So does that series converge or diverge, and why?
Diverges
It diverges, why?
because it goes bigger and bigger.
It gets bigger and bigger, right? So remember the nth term test for divergence? If you look at the sequence, right? This is the sequence inside our series. If you take the limit of that as n goes to infinity, if it turns out to be something not 0, what do we conclude?
Divergence.
It diverges, right? So this is a divergent series, but I have to plug 2 in order to determine it's divergent. What would happen if I plugged in 4? So if I replace the x with 4, what would happen to that series?
Divergence.
It would diverge also, right? I'm just going to put diverge. Same reason it diverged at 2. But what if I plug in a half? Wouldn't that be like this? Can somebody tell me what kind of series that is?
Geometric?
Geometric. That's a geometric series. Now remember, I told y'all a long time ago that when, oh, geez. I told y'all a long time ago that when it comes to geometric series, sorry, that's sloppy. There were 2 formulas for it. One of them started at 1. And the other equivalent formula was that it started at 0. Do y'all remember me telling you that or no?
Yes.
Yes.
So we are actually looking at this one right here because it starts at 0. Do y'all see that that formula is exactly what we're looking at right here in the yellow?
Mm-hmm.
What's A for us here?
1.
A is a 1 sitting right in front there. And then what is our R?
Uh-huh.
A half. And the absolute value of R is less than 1. And that's what makes a geometric series converge, right?
Mm-hmm.
So in this case, this converges. Not only do we know it converges, we know what it converges to. What does it converge to? A over 1 minus R, right? Which would be 1 over 1 minus a half, which would be 1 over a half,
2.
which is 2. Yes? Okay. What about this one? I know this, I didn't give myself enough room here. What about if we do the series and we plug in -1/2?
Be the same
What
thing.
will that do? What's that?
It'd converge because it's
It
absolute
also
value.
converges, right? Geometric?
Yeah, but it would converge to 3 halves, right?
Yep, it would converge to a over 1 minus r, but r is actually negative a half, right? Oh, a is 1. Ah, come on. Sorry about that. So this is 1 over, I didn't put the negative in there, negative.
1 over 3.
This is starting to really irritate me. Negative, so that's going to be 1 over 3 halves, right? Which is
2/3.
2/3. What about a negative 1? Sum n equals 0 to infinity, negative 1 to the n. What does that do? And why?
Diverge. Because
Diverge.
it's constantly flipping between 1 and -1.
That's right. It diverges because the limit, you can do the nth term test here. Do the limit as n goes to infinity of -1 to the n, that's definitely not 0. So it diverges. Okay. Now, we've reached a profound moment. We've reached a profound moment. As we can see, convergence of the power series depends on the choice of x, right? It depends on what we choose. For this particular example, so you have to remember, I'm giving you just one particular example of a power series. This is not every power series. This is only one particular one. And in this particular power series, the convergence or divergence of it all depends on the x that you plug in. If you give me the x, I can tell you whether or not it converges or diverges. In fact, if you give me the x and it converges, I can tell you what it converges to. So we can see that the convergence depends on x. In fact, if we choose an x which converges, we can assign a value to the series. So take a look at this little diagram I have. You give me an x, I do the power series of it. If it converges, that series is a number, isn't it? Yes? Does that look like something you've dealt with in your life before? Input, output?
Functions.
Functions, right? What we're saying is this series, this power series, maybe we can look at it as a function, right? In this particular case, with this particular example, what would f of 2 be? What happened when we replaced x with 2?
X minus, or 2 minus x squared.
No, remember this? If x was 2, what happened to the series?
Yes.
It diverged.
It diverged. So if f of 2, what would happen? That would be undefined. Okay, just hang on with me here. What would f of 4 be? Undefined, right? Because our series diverges. What would f of 1/2 be?
2.
Now that converged, right? So what would that be? What did we get when we did that? Didn't we get 2?
2.
2, okay, so we got 2, great. What happened when we plugged in -1/2? We got
2/3.
2/3, okay. What happened when we plugged in -1?
Undefined.
Undefined. Okay, what the hell's going on here? So we have some places where things are good, right? Green, that was all good. Our function is well defined. And then we've got places where our function is undefined, which means that I want someone to make the connection here. Can someone, just wondering if anyone sees what I'm about to say.
So does it have a domain?
Ah, there we go. We're talking, this function has a domain. Think about this. Think about this function. College algebra, square root of x. Is everyone comfortable with the idea that we can plug some numbers into this and some we can't?
Yeah.
Yes, sir.
Okay, so we know that when you have functions, sometimes the inputs work and sometimes they don't. Well, we just discovered that if we want to look at a power series as a function, then there might be some issues with the domain. Some numbers you replace x with are going to work and give you a number answer, and some will not, which is the way functions behave. You have domains, and sometimes, you know, sometimes those domains are everything, and sometimes they're just part of the number line. Could you tell me, at this point, could you tell me, with this still in this particular example we're looking at, this one right here, can anyone tell me what the domain of this would be if I actually looked at this as a function? For what values of x would this thing actually spit out an answer?
From
So
0
what
to
would be
1?
the domain of this?
Either
What's
1
that?
half to 2. Either 1 to 2.
Say again?
Somewhere between -1 and 2, wouldn't it?
-1 and
1.
1, right? Because wasn't it really behaving like a geometric series? And that right there was really like the R. That was like the R in a geometric series, wasn't it? And what do we need for convergence? We need the absolute value of R to be less than 1. So the domain for us is anytime the absolute value of x is less than 1. So let me recap. If the absolute value of x is less than 1, then would you agree with this? I've been teaching this for too many years, and I never stop getting excited about just how awesome I think this is. If the absolute value of x is less than 1, then what can you tell me that that infinite power series is equal to? Drum roll.
Convergent.
It is convergent, but to what?
0?
No.
Okay.
I didn't hear that last piece. So when we plugged in 1/2, right? What did 1/2 go to?
2. 1 over 1 minus
2/3.
Yeah, it went 1 over 1 minus 1/2, right? So as long as I'm picking an x that is the absolute value is less than 1, shouldn't this be equal to this?
A geometric series? Or?
Yes, but it is the geometric series. But what I'm trying to get you to see at this point is that this right here is a function, isn't it? Haven't you seen a function like that, let's say in college algebra? That would be a rational function. I'm telling you that this infinite power series is equivalent to that so long as we are looking in this domain. All right. I got to show you a picture of this, all right? So I'm gonna take this stuff out. Okay, let's just kind of start from scratch here. Let's do 1 divided by 1 minus x.
That's pretty cool.
And I'm going to zoom in on this. Okay, there's the graph of 1 over 1 minus x, all right? Now, we just said that so long as you're looking in the window -1 to 1, is absolute value of x less than 1 means you're somewhere between -1 and 1. Do you all agree with that? Yes?
Yes, sir.
Okay, so what I'm going to have here, I can just type in sum n equals 0 to, let's go to m, and let's go x raised to the nth power, right? And it's too far out. All right, so right now, what you're looking at there, let me change this because I want that slider down here. Let's make it to t. T. Okay, so this black function here, this black function, you see that blue curve? That's not a very good approximation, is it?
No.
Can anyone tell me what that blue curve is there? It's not a curve. It's a straight line, right? That's just one, isn't it? And isn't that in this power series? Isn't that just this first term? Yes.
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 Okay, so let's go back. Let's go now and move out a little bit more. So let's add that second term. See that line? That's the line 1 plus x. Okay, let's go a little further. Let's go here. That's now 1 plus x squared. And if I drag this slider across, this blue curve is going to get better and better. Now just watch what happens. Do y'all see that? Look, between -1 and 1.
Why doesn't it
Negative
give
one
the
and
other
one.
curve?
Pardon?
Why doesn't it give the other curve as well?
Because what is, okay, you're asking the perfect question. This is what I want everyone to understand, is that this blue curve is a really good approximation of the black curve, only within this little window, right? It doesn't do a good job outside of -1 and 1. And that's because we said that would happen, right? This series only converges to this value if the absolute value of x is less than 1, right? Yay or nay?
Right.
Yep.
Okay. So you might be saying to yourself, well, that's not really helpful, because maybe I would really like to know what's happening over here, right? And I'd like to have an approximation. Well, I can just change one thing here. If I change, do you remember we said power series about A, right? About A. That was about 0, but now it's going to be about, actually want it to go the other way. Oops, +1. So do y'all see what happened to that? See it moved over? And hold on a second. This is really not good. Minus, hold on. Hold on, I'm missing something. Hold on, let me just think about this. No, it's only good about 0.
Are we missing something outside for C?
No, I have to shift both of them. We're going to do this. We're going to move these things over so that it's valid in a bigger region. For now, let's just be satisfied with the fact that we have a way of approximating that function, at least within this little window. The main thing I'm trying to get you to see here is kind of like what I tried to convince you with the sine. You know, we said sine x is approximately equal to -1/6 x cubed plus x. And if we were able to go out further, you could say that it's equal to this infinite power series. I've just given you another example where we have some function, right? That's not sine x, that's 1/1 minus x. But we actually have come up with another way of representing that as an infinite power series. And that is so crucial to mathematics, this connection right here. Because what we learn later, and it's actually called the Weierstrass theorem. Let me bring it up because I don't want to say it and misspell it. Weierstrass. I can't spell it. Yeah, messed that up. So let me just kind of read through this. The Weierstrass approximation theorem states that every continuous function defined on a closed interval can be uniformly approximated as closely as desired by a polynomial function. That means as long as you are dealing with a function that is continuous, that means it doesn't have any crazy jumps or breaks, you can always approximate it with a polynomial, always. And That's exactly what we're doing right here. It's exactly what we're doing. We're saying, hey, look, this function, right, is continuous, not everywhere, right? But it is continuous, at least not at 1, right? Everywhere else, everywhere other than 1, it's continuous. So I should be able to approximate it by a polynomial. Well, here it is, you know? Here's the polynomial. The sine function, I can approximate that as close as I want with a polynomial. How would I get better approximations? I just go further out into this series. Okay. Let's just take a deep breath. Anyone have any comments or questions or anything up to this point that I need to clarify?
So is that series what gives us the function on the right side, basically?
Like the egg and the chicken, kind of? Is that what you're saying?
Yeah, I think so. Yeah.
That's
'Cause
that's a great question. If we go back to, where was it? Okay, to approximate a given function at x equals a with a polynomial, we only need to know the value of the derivatives of the function at x equals a. So I think that answers your question. You can't generate the function, okay? You can't generate the function, the polynomial, without knowing what the derivative of the original function is, but you only need to know what's happening at a single point. Does that make sense, Alex? It's saying to generate the power series, you only need to know what all the derivatives of the function are and what the value of those derivatives are at a single point. To me, that still blows my mind, because like if I tell you right now that I have a function, let's say that goes through this point right here, and I can tell you it goes through that point. I can tell you the first derivative at that point, second, third, fourth, fifth, sixth, seventh, eighth. If I can just tell you about all the derivatives at that single point, then I can approximate the function nearby with a polynomial.
Yeah, that's pretty crazy.
That's crazy. That's crazy, but that's what it's saying. So
Just with 1 point.
to be clear on the answer to your question, you cannot generate the power series without knowledge of the original function. So,
Right.
but what we learn later is once you generate the power function, you can replace the original function with it. So like sine of x, I showed you here a second ago, sine of x, you can use this as the definition of sine of x. It's perfectly valid. Now you needed this to create it, but once you used sine and all its derivatives to create the power series, you no longer need sine. Now, why would we want to have a power series? Like, you know, what's the value of having a power series over just the original function? Like, you know, sine or whatever, you know, sine of 4. Why not just use the calculator and not even worry about the power series? Well, computers, right? Computers can do this arithmetic easily. You can have a computer plug a number into this for x. And that's exactly what happened when you typed in sine of 1 on your calculator. It did not do anything other than plug 1 into this power series, and it stops somewhere. In the code, someone who wrote that code in your calculator told the computer to stop at maybe x to the 10th, or 9th, or maybe x to the 21st power. And it says, okay, stop, and just spit out that answer. But the calculator has no idea what the sine function is. It just looks at it as a bunch of multiplications and additions and subtractions. Because that's all your calculator can do, right? That's all your computer can do.
But wouldn't that mean that there's a bit of error between the actual real-life answer from the calculator?
Yep, absolutely there will be error. Because you can never take an infinite sum, can you? I mean, you can't, right? There's no way for you to do an infinite sum. You would be there forever. But is that a problem? Well, let's just think about pi. Don't we approximate pi? I mean, pi goes on forever, right? 3.1415. I mean, that goes on forever. And if you need to use that in a calculation, let's say, Hogan, you're building aircraft ball bearings, right? Like pi is going to be in there somewhere. It's a sphere, right? A ball bearing is a sphere. Pi is going to be there somewhere. Do you think that the aircraft manufacturers have, do you think they round pi to 3.1? Probably not, right? They probably round pi out, to a certain precision. So approximations are perfectly fine in the real world, aren't they? Would you all agree?
Yeah, as a pilot, everything is rounded up.
Yeah, it just depends on how precise. Like if I'm making ball bearings for an aircraft engine, right? We've got those tolerances on that manufacturing process are like in the tens of thousands, like 10,000ths of an inch or whatever, millimeter. It's super precise. If you're making a tricycle for a 5-year-old, your ball bearings can be complete junk, right? You don't have to be precise. If the wheel falls off, the wheel falls off, right?
Well, then somebody gets hurt and the company gets sued, but.
Yeah, but I'm saying even then, right? Even then, those ball bearings can be so out of whack, it'll function perfectly fine for the life of the tricycle. You have one bad ball bearing in an aircraft engine, and that plane's coming out of the air, And so when you talk about, this idea of a series as being an approximation, I know that that's not easy to swallow because you're like, well, wouldn't the exact be better? But even if we have exact answers, when you go manufacture something, you can never get it. There's always going to be an error, always. There's just no way. It's like, think about a soda can sitting in front of you that says it's 12 ounces. Do you think it's exactly dead on 12.000000 forever?
No.
Hell no, right? It's within some certain precision, and that's it, and you're satisfied and move on. And that's the way the real world works with engineering and everything else. And so that's why these series are so great. And we haven't even started talking about what makes them great in terms of taking derivatives and integrating, right? So I'll give you a real basic example. If I ask us to integrate this right now, okay? What's that going to take? And let's say we wanted to go from like 0 to 1. What is that integration going to take from us?
Integration by parts?
Integration by parts twice, right? Okay, so you know what? Instead, I'll make that 20th power. Integration by parts many, many times. Do you submit yet? Do you submit? Okay, you don't submit, 200. How about that? Okay, I can make you submit, yes? But if we know that the sine function is approximately -1/6 x cubed plus x, right? That's what it is, approximately. Then can't you just distribute this through? And that's just integrating powers. And isn't that easy to integrate powers?
Yeah.
Yeah, and if you weren't happy with that and that wasn't precise enough for you, then you could go, and maybe pick the first 5 terms of the power series. Does that make sense? And if that's not good enough, so you would have, I think it would be 1/120 x to the 5th minus 1/6 x to the 3rd plus 1. That would be if you went out 3 to a 5th degree polynomial for sine. But that's still something you could integrate, right? You all follow that? Distribute?
Yep.
And so with power series, you're making very difficult integrals easy. As long as you're willing to wave your hands a little bit and say, yeah, I'm going to be off a little bit, but I can be as precise as you ever want me to.
So quick question.
Yeah.
So if we do that, we take the sine, convert it into its power series, perform the integral, would we ever have to revert it back into the new power series for, say, cosine? Or to turn it back from the power series into cosine times whatever?
I'm not sure I understand your question. Like, okay, so we get an answer here and then take that answer and somehow realize, oh, that's cosine.
Right, and then, right.
No, not if, we are not going to have to do that, okay? We are not going to look at a power series and be like, oh, that's obviously this. And normally, I'm trying to think of when that might come up. I mean, I know that there's times in physics and engineering where you're working through something and you see a series, right? You'll get like 1 plus, x, blah, blah, blah. And you're like, oh crap, that's cosine x, But we're not going to be doing that. Our whole thing is, can we take an integral that would really be tough to do, if not impossible? Can we make it easy with this? And the answer is yes, we can.
Gotcha.
Okay. I think we need to get back on track. I'm not off track. I'm taking a lot of time to go through this. All right, so let's take a look at a second example. So there's a new power series. Sum n equals 0 to infinity, n factorial times x to the n. Now, next to this, I'm going to write the example we just did so that you can see the difference. Okay, that's what we've already looked at. So what's the big difference here?
N factorial.
The n factorial, right? So this right here is our c sub n. Our c sub n is no longer a constant. Our c sub n changes. It depends on what n is, right? So let's write down what the series is if we start plugging in values. So n goes in, you get 0 factorial x to the 0 plus 1 factorial x to the 1 plus 2 factorial x squared plus 3 factorial x cubed plus 4 factorial x to the 4th plus dot, 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 dot. Which is really just 1 plus x plus 2x squared plus 6x cubed plus 24x to the 4th plus dot, dot, dot. Y'all see what I'm doing there? Just turning those factorials into numbers. These are my coefficients. Oh yeah, remember 0 factorial is 1. We had that conversation?
Yeah.
0 factorial is 1. Okay, is that a geometric series?
No. Well, yeah, it still is, right?
I'll remind you over here what a geometric series looks like. Sum n equals 0 to infinity of a times r to the n, right?
It does, right? It is. Or
So
does A
what
have
was the thing about a in this formula? That
It's a
a had to
constant.
be a constant. It could not change, right? It had to be consistent throughout the entire sum. And in this case, our coefficients always staying the same.
No.
Yeah.
They are not. So this is not geometric. Now let me ask you this. For what value or values of x does this converge? Well, how did we answer that question on the previous example? This example up here in blue. How did we answer that question on the previous example about its convergence?
The nth term test.
Ratio test.
Yeah, but we realized it was geometric, didn't we?
Oh, yeah.
Said, oh, it's geometric, so the absolute value of x needs to be less than 1, and we're good to go. Agreed? We can't do that now because it's not geometric. So I'm going to just take a quick 30-second break. I'm going to have you think about how you can answer that question. And then I'll be back and I'll ask, and I'll see who's got it.
Is it possible to take a limit of a factorial like that?
Yeah, remember when we did the factorials, you just expand them out so you can cancel out the
Yeah.
factorial.
What are y'all thinking?
Do a ratio.
Ratio test?
Ratio test.
Yeah, that's what I was thinking as well.
Let's do a ratio test. So how am I going to figure out whether or not this converges for what values? I'm going to do a ratio test. And the ratio test says that we will be taking the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's our good old ratio test, isn't it?
Yeah.
For us, a sub n plus 1 is actually this in pink replacing n with n plus 1, and we're just going to leave x alone, right?
Yeah.
So what should it be? N plus 1
factorial.
factorial x to the n plus
N
1
plus 1.
over n factorial x to the n. Now, we have never done a ratio test where we had x's here, right? This is different. But don't worry, it's all going to be good. We're all going to be happy at the end. Okay, let's clean this up. This is the limit as n goes to infinity of n plus 1 times n factorial. I'm peeling off an n plus 1 on that top one. I'm rewriting x to the n plus 1 as x to the n times x. And I'm rewriting, well, I'm not rewriting the bottom, I'm just leaving it alone. Everyone see what I did there algebraically?
Yes, sir.
Okay, see all this nice cancellation that happens?
Yes, sir.
What you're left with now is the limit as n goes to infinity of what?
N plus 1.
N plus 1 times
X.
x, absolute value, right? Okay, let's just take a deep breath here. What was it that the ratio test said? It said if we take this limit and we get what?
Less than 1 converges, greater than 1 diverges.
Yeah, if this thing turns out to be a number less than 1, this thing will converge, and if it's greater than 1, it'll diverge. And what if it is 1?
Inconclusive.
It's inconclusive. Okay, so now how do I explain this? Remember when we were doing the problem with the series sum, this one x to the n equals 0. When I first motivated that, I said, what if x was 2? And everyone said, oh, it would diverge. And I said, what if x is 4? And everyone said, oh, it would diverge. And I said, x is a half. And we said, oh, then it would converge. X is negative a half. We said, oh, it'll converge. If x was negative 1, we said it'll diverge, right? So these were the only two that converged.
Mm-hmm.
We were plugging in an x and seeing what happened, right?
Mm-hmm.
Plugging in an x and see what happens. So imagine right now that you were to fix this x, okay? Fix it right now. It's a number, okay? It's held as a constant. Take your limit now and tell me what happens.
Goes to infinity.
Goes to infinity, doesn't it?
Mm-hmm.
Yeah, yes, I agree, but there is one thing we could do to prevent it from going to infinity. There is one value of x that I could pick that would totally kill the n plus 1.
0.
If x was 0, right?
Yeah.
So if x was 0, this thing would be 0, and that would be less than 1. But if x is anything other than 0, then it's going to diverge. So I'm going to state that if x is equal to 0, then the limit as n goes to infinity of n plus 1 times 0 will equal 0, which is less than 1, which means we have convergence. But if x is not 0, anything other than 0, then that limit, as n goes to infinity, of n plus 1 times x will diverge. Any questions on that?
That's the answer?
Well, I was about to ask you, for what value or values of x does the series converge?
Zero.
Zero.
0.
0 to 1.
I want to go back. For this power series that we did a little while ago, for what values of x would this one converge?
The absolute value of 1.
The absolute value of x has to be less than 1, then it'll converge, right? So visually, for this power series here, visually, on a number line, so long as we plugged in numbers that were between -1 and 1, that series would converge. Yes? What are we saying on this example?
That only that one point converges.
Yeah, this series right here only converges, if you look at the number line, it only converges at one point. So I was trying to get you to see that the values of x for which the series converges is like a domain. And so in this particular example, the domain of this function is a single point. This function is only defined at 0. That's it. That's it. That's it. That's a weird function. You can only plug one number into it, and that's 0, and that's it. In this example, the domain was what? Not a single point, but what? What is this? What do we call
Negative 1 and 1.
Yeah, but what do we call that? It's not a single point. This would be a what?
Inequality.
You could look at it as an inequality, but on the number line, this is just an interval, isn't it?
Right.
It's just an interval. So far, in the two examples I've shown you, we've had where the values of x for which the series converged was an interval, and we've also had an example where the only place the series converged was at a single point. All right. You ready for the last example? That's all I'm going to have time for today. Third example. And we may as well go big. Let's go big here.
When you said on the first example, it only converged at an interval.
On an interval.
Interval. Okay.
Interval.
Yeah. Okay.
Interval.
I was going back trying to find an integral. I was like, I don't remember.
Interval. And then we also had it at a point. That's what we've had so far. In the two examples that we've had, in example 1, it converged on an interval. In example 2, it converged at a point, right?
Yes.
Okay, let's look at a third example. And I'm going to pull this one. Are you ready? You're gonna get nauseous when I put this down.
Uh-oh.
Sum n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over n factorial times n plus 1 factorial times 2 to the 2n plus 1. This is called a Bessel function of order 1. Order 1. Do y'all want to know? So I hope that maybe you've taken away from today that a power series at some point actually just becomes a function. Have y'all kind of grasped that idea?
Right.
Okay, so what do I have here? Someone's chatting. 1 or 0? What? Al, what you got?
Is that order 1 or 0?
Order 1.
Oh, okay, I'm sorry.
That's an order 1 Bessel function. So let's look at an order 1 Bessel function. You want to see how where these are used?
No, it's okay, sir.
No, I want to see it. I was going to do this anyway. Bessel functions are the first kind. Let me see. The Bessel functions of the first kind are defined as solutions to the Bessel differential equation. This really wasn't what I was looking for. Wikipedia. This is like the layman's. There we go. So like Bessel functions are used to model vibrations on any circular type drum. If you want to model the behavior of the oscillations, you have to use a Bessel function for that modeling. So I'm just giving you an example of where they're used. See if they have anything else here. Nothing visual. This is all, yeah. So drums, vibrating, just think Bessel function, think vibrating drum. Now, the question is, for what values of x does it converge? Value or values of x does this converge? And I really want you to start thinking about this question as me asking you, what is the what? What do you think?
Domain.
What is the domain? What is the domain of the function? Okay. What should we use?
Ratio.
The almighty. Let's please use almighty. I don't want to have to take off.
The almighty ratio function?
Just kidding. The almighty ratio test. Here we go. Ratio.
Ratio test.
Test. A quick little head bow, and we proceed. Limit it. N goes to infinity. All right. I need to basically take this big ugly thing and replace all the n's with n+1s.
That's real ugly.
Now I'm gonna ignore the -1 to the n, because when I take the absolute value, that's not gonna matter, right? So I'm gonna get x to the 2 times n+1 plus 1 over n+1 factorial times what? So I'm replacing all the n's with n+1s.
So it's n+2 factorial.
So that'll become n+2 factorial. And then I still have down there 2 to the 2 times n+1 plus 1.
Gosh.
But all of that over
The original.
just the original thing. X to the 2n plus 1 over n factorial n+1 factorial 2 to the n plus, sorry, 2n plus 1. All right, I just got to figure out what that does. Does that look terrible or what?
Yeah.
Maybe a little algebra first? All right, here we go. So this in yellow really becomes, what, 2n plus what? 3?
Plus 3.
Right? So does this one. This becomes 2n plus 3. All right, let's just write it down. Here it goes. I've got x to the 2n plus 3 over Okay, so I've got this taken care of. Now I'm working on this denominator. Yeah, I'm just going to write it down. N plus 1 factorial, n plus 2 factorial, 2 to the n, 2n plus 3. Right? But then I'm going to divide that by this thing, which is the same as multiplying by the reciprocal.
Right.
So I'm going to put n factorial here, n plus 1 factorial here, put 2 to the 2n plus 1 there, and then on the bottom, I'm going to have x to the 2n plus 1. We need to get stuff to cancel. Does anything cancel yet?
Your
Plus one
factorial.
Yeah, the n plus 1
Factorials
factorial.
are gone. Okay. Is there anything I can do with this n factorial to make it go away?
Break apart the n plus 2 factorial into n plus 2 times n plus 1 times n factorial, and then cancel out the n factorials.
Perfect. There it is. Bam, bam. Y'all good with that?
Yes.
Okay. How about this piece here? Couldn't I rewrite that as 2 to the 2n times 2?
Yes.
And I
Yes,
could
sir.
rewrite this as 2 to the 2n times 2 cubed. Yeah?
We could do it with the x's too.
And I could do that with the x's too. So this could become x to the 2n times x cubed, and this one would become x to the 2n times x. And then we get a bunch of stuff to go away, don't we?
Mm-hmm.
Let me get rid of these I've rewritten. So what goes away? We've got x to the 2n's gone. We've got 2 to the 2n's gone. Anything else cancel? I could reduce this, right? X cubed over x could become x squared. Everything else is still there. Oh wait, I can do it 2, can't I? I can do it 2 over 2 cubed. That's just going to be a 4 on the bottom, isn't it? This ain't so bad. Okay, limit n goes to infinity. Oh, okay. What is left in the numerator? Do I have anything left in the numerator?
X squared.
X squared.
X squared. Okay, so I have an x squared up top. And on the bottom, I have
N plus 2.
Plus 2.
that became a 4 on the bottom, didn't it?
Yeah, you got 4 times n plus 1 times n plus
4
2.
times n plus 1 times n plus 2, right?
Yes.
And that's it. I believe algebraically that's what it cleans up to be. Now, this next step, I like to do this next step because I think it helps make things clear.
And it.
I like to separate my x's and my n's from one another. Because remember, we're gonna try and fix the x, right? Just like pick a value of x and then take the limit and see what happens.
X squared.
X squared, yeah, thank you, x squared. So what happens, everyone? If we fix x right now, what happens?
0. X is
We
0.
get 0, don't we? This thing right here heads to 0, doesn't it?
Yes.
No matter what we choose for x. Give me any value of x. Give me a billion squared, and then I start letting this thing head to 0. It's gonna be. This is always gonna be less than 1, isn't it? No matter what.
Yeah.
Check always. So if you can pick any value of x, that means that the domain of this function is what?
Negative infinity.
0?
Negative infinity to infinity, which is just, you know, all real numbers. So for what values of x? The question was, for what values of x does this infinite series, power series, converge? Our answer is all real numbers, all values of x. We're almost out of time. Let's recap. For convergence of a power series, what are the 3 different results that we've had so far? In our first example, it was an interval. In the second example, it was just a point. And in the last example, it was what? All real numbers, right? Visually, we had an interval. We had a point. And we have, well, everything, right? Both directions forever. We don't have enough time to get into this any further. We're going to have to pick up on this a little bit next time. But it turns out that there is a theorem that says for any power series, you can only have one of those 3 things happen. That's it. Those are the only 3 things possible. Give me any power series, and it's either going to converge on an interval, at a point, or everywhere. So that theorem we'll have to pick up on next time. So what I want you to do is I want you to try and go through, make sure you've watched the video for 8.5. Start trying to do the homework, but I have not talked about some important concepts here, specifically something called the radius of convergence and interval of convergence. So I anticipate we'll start class next time with a discussion about those 2 things, radius of convergence and interval of convergence. But see if you can't watch my videos and make sense of it. I think you can. And then we'll move on to the next section. Man, we still have so much to do.
So that would be day 24, correct? Or 25?
Video-wise?
Yeah.
No, I don't know. Let's see here. Yeah, make sure you've watched day 23 and 24. Make sure those are both done.
Gotcha.
This will just be an introduction into the functions as power series. I've already kind of started to allude to this, you know, but you can write a function as a power series, and that's what 8.6 is about, or 8.6. All right, so that was fun for me. I wish that you could, I wish we were in a classroom, because, I mean, it's so hard to communicate my enthusiasm over this internet. But how did this feel to you all?
Oh, better.
Interesting.
Yeah, this is a really, really interesting part of math right here, this part of calculus, because you're really, you're stepping away from things that are normal, starting to realize that all these functions you've dealt with your whole life, there's another way to represent them. And in the real world, that's what we use most of the time. Because things get complicated. It's just easier to work with the power series than it is the functions. So, okay, well, I guess have a good weekend. Right, it is
Thanks,
Thursday.
you too, sir.
Have a good weekend, and
You want us to turn in anything by Sunday?
pardon me?
Do you want us to turn in anything by Sunday?
You know what? I mean, you know what I'll do, because that test score, the test score averages were pretty low. You know, those 2 problems that I asked you to do as a quiz, let's just treat those as a bonus. I want you to keep up with what's going on. I don't want you to be spending too much time on that stuff. So if you want to do those 2 problems and turn them in as a bonus for the exam, that's fine. And let's just say you need to do that, you know, before class next time we meet. Okay?
Okay.
Gotcha.
All right, sounds good.
All right, everyone.
All right, quick question. Are you going to be posting this video, or are you just going to refrain from doing that because of
Well,
scores closer.
I flashed everybody's grades up there for a moment, and so I'm a little bit hesitant.
There's
to
no
do
way
it.
to edit that out.
I think there is an editor. Let me see how easy it is to edit, because it's in the cloud. The video's in the cloud, so I don't know if Zoom has some editing software in the cloud. I might have to download it and trim it and then you know, put it back out there. But I'll work on it because I think that was a beneficial lesson. I think there are a lot of things we covered that are important there. So I'll do what I can to see if I can edit it.
Sir, I wanted to just mention to you, I got those two problems turned in. I redid the problems. Like I did them a second time to get the correct answer, but I turned in both basically the scratch work or the non-correct and the correct versions of the work.
Two different emails?
No, it's all the same email.
Oh, okay. All right, well, I'll look at it.
Okay.
Thank you.
Yeah, I just wanted to let you know of that.
Yeah, okay.
Would we
Go ahead.
Would we submit this bonus one under quiz 10?
Yeah, I think some people already did that, so let's just do that. Just submit it under quiz 10.
Thank you.
If anyone wants to talk about the exam, I can do a breakout room and put you in a breakout room, and then we can, if there's anything on the exam you want to discuss, not with everyone else around, I'm happy to do that. Just let me do this. I think it'll be easiest if I just make breakout rooms. And if you're happy, you're free to go, whatever. Okay, so.
All right, we'll talk to you Tuesday, sir.
Okay, so I've created 21 breakout rooms, and what I can do is I can kind of, if you want to go into the breakout room you're invited to, you can, but then it's going to take me a while to get to you if I go through everyone. So you'll just have to be patient.
Hey, Mr. DiGiovanni?
Yes.
Did you curve the test?
I have not curved the test.
Okay, because the grade you texted me was different from the grade that I saw on the screen, on the display chart you showed up.
Really?
Yeah, it was.
Like way off?
No, not way off, just like 4 or 5 points. So I was wondering,
Oh,
like,
really?
regraded it.
I'll go look at it. Let me stop sharing my screen.
Because I think I found my name on the line or whatever, but I couldn't be sure if it was mine. But I just looked for, the one you're telling me about.
Let me see here. Y'all can't see my screen, right?
No.
Yes, sir.
Okay, so what did I text you? Where's my phone? Almost there. Hold on.
Mr. DiGiovanni? For the breakout rooms, are we discussing the exam in general, or are you discussing your exam, like individually?
I'll discuss whatever. Like if you want to talk about your test or anything related, it's just an opportunity if you want to speak in private about something.
Are you gonna put out an answer key for the exam?
I will. Yes, I will.
Oh, okay. Thank you.
Okay.
All right.
Jackson, I'm looking at the text I sent you,
Mm-hmm.
and it's the same number as what I see on the Google Sheets.
Oh, okay. Because I just saw, I didn't get a good look at the display chart you shared earlier. I just looked for like the rank you told me that my grade was, and so the point value looked off, if I remember correctly.
Yeah, let me see. Let me just, this is what I have.